We now have achieved our goal of understanding the motions of the sky, predicting which stars will be visible, which season, where on Earth, at what time of the night. Um, there are some other things we'd like to understand. We talked about the orbital motion of the Earth and how it affects which stars are visible in the sky when. Of course, there's another phenomenon on Earth that repeats with a periodicity of once a year, namely the variation of the seasons. The climate on Earth changes once a year, and in fact, the original interest in astronomy, much of it, was derived from the fact that by understanding or watching which stars were visible in the sky, say early in the evening, you could predict the coming of harvest time or the time to sow or the inundation of the Nile or whatever, all other phenomena that were periodic with annual periodicity because they depended on the seasons. And the reason why the Earth's orbital motion is related to seasonal changes in temperature, of course, has to do with the fact that if you ever see one of these globes, it's always depicted in a tilted version. We all know that the globe is tilted by, oops, I had it upside down, tilted by 23.5 degrees. But this is interesting, we're out in space. 23.5 degrees with respect to what? Well, it turns out that the globe is tilted by 23.5 degrees relative to the plane of the ecliptic, the plane in which the Earth orbits the Sun. In other words, if I want to imagine that the Earth orbits the Sun in a horizontal plane, then I must hold the globe tilted by 23.5 degrees rather than vertical, with the north celestial pole, therefore, off in that direction, 23.5 degrees away from the vertical. Contrariwise, if I want to present things with the north celestial pole vertical above me, then the plane in which the Earth orbits the Sun, and of course the plane in which the Sun appears to orbit the Earth, will be tilted by 23.5 degrees away from the horizontal, because it was horizontal in this frame of reference, and now I've tilted everything 23.5 degrees this way. So that the Sun's orbit around the Earth, or the Sun's motion along the celestial sphere, is not along the celestial equator, but along a circle tilted 23.5 degrees with respect to the celestial equator. This trajectory of the Sun moving to the east along the celestial sphere is called the ecliptic, and it's a circle tilted with respect to the celestial equator by 23.5 degrees. And if you take two circles and tilt one with respect to the other, they're hinged, so there are 2 points at which they continue to meet. Those are the points where the hinge meets, and so those 2 points are the points where the ecliptic meets the equator. Those are the positions along the Sun's motion when it is along the celestial equator, and the names of those points are the vernal and the autumnal equinox, for reasons we'll talk about in a minute. And these, it turns out, are the positions which by convention we chose to define the prime celestial meridian of 0 hours of right ascension. So when the Sun is at the vernal equinox, it is at 0 hours of right ascension. This means that the Sun is overhead at sidereal time 0. Sidereal time is off from solar time by 12 hours, and so the Sun is at the vernal equinox, if you look back at the last lesson, on March 21st, and it is at the autumnal equinox 180 degrees away 6 months later at 12 hours of right ascension on September 21st. So March 21st and September 21st are the days of the year at which the Sun is along the celestial equator and has celestial declination 0. And between those two, after the Sun passes the vernal equinox, it moves into the northern hemisphere of the celestial sphere, and its declination rises until at the full apex of its tilt, its declination is 23.5 degrees north, and then this happens on or around June 21st. Then it goes on September 21st, it meets the equator, and on or around December 21st, the Sun's is farthest south that it goes, its declination is 23.5 degrees south. And let's see how all of this relates to what we understand about the seasons. This demonstration will explain to us what the tilt of the Earth's axis, or equivalently of the Sun's motion around the celestial sphere, has to do with our seasons. So what we have here is, here's our celestial sphere view. The green line is the celestial equator. The tilted line is the ecliptic, the motion, the line in which the sun moves around the celestial sphere. And what we are seeing is that the sun is located now at the line of 0 hours of right ascension. In other words, it is the vernal equinox. This is the position of the sun on March 21st. Notice that on March 21st, the sun is at 0 hours at sidereal midnight, and so it's sidereal midnight when the sun is overhead. In other words, when it is noon. Indeed, sidereal time is off from local time by about 12 hours at the vernal equinox. So this is the position on March 21st. The sun is on the equator. What this tells us, if we switch to an orbit view, is that the Earth's tilt at this point is such that the sun is neither north nor south. In other words, the tilt is perpendicular to the direction to the sun. And if we look from above, we see that as the Earth rotates about its axis, the line separating day from night, the sun side from the dark side of the Earth, goes right through the North Pole and equivalently through the South Pole. So over the course of a day, every point on Earth spends a half of its time on the sun side in daylight and a half of its rotation on the dark side at nighttime. Hence the word equinox. Night and day are equal length everywhere on Earth, and this happens whenever the sun hits the ecliptic. In other words, on March 21st, when the sun is at the vernal equinox, and again 6 months later on September 21st, when the sun is at the autumnal equinox. Now, what happens as we, moving back to the celestial sphere, as time goes by, the sun moves around not the equator, but the ecliptic. So a few months later, the sun is now north of the celestial equator. Its declination at this point, its right ascension is 3 hours, so let's move it a little bit more. Its right ascension is 4 hours. That means that about 2 months have passed. It is now, if it was March 21st, it is now May 21st, and the sun's declination is 20 degrees north, which means the sun is well north of the celestial equator. That means that the sun is directly overhead at a point of terrestrial latitude 20 degrees. You see the direction from which the sun's rays are reaching Earth, and you see that the line separating dark from light on Earth no longer goes through the poles, but that in fact a whole region around the North Pole is encircled such that it is always in the sunlight. If we look from the sun, we will see that this whole region around the North Pole is always visible from the sun, and therefore as the Earth rotates, the sun never sets at the pole or points sufficiently close to the pole. And the sun impinges overhead at latitude 20 degrees, and as we move the sun farther along the ecliptic, it reaches its northernmost point in June, on June 21st, when the sun's declination is 23.5 degrees. The sun is now at the point where it's maximally north on the celestial sphere. What that means from the point of view of the orbit is that the Earth's North Pole is tilted, the direction in which the Earth's North Pole is tilted, which is always toward in the same direction, is now the direction of the sun. So now points all the way to within a circle of 23.5 degrees latitude around the North Pole are visible from the sun and therefore have continuous sunlight throughout 24 hours, whereas a full circle of radius 23.5 degrees around the South Pole is invisible to the sun, and the sun never rises there, and the sun is overhead at the tropic of Capricorn, the north of Cancer, the northern tropic, where the sun is overhead at a latitude of 23.5 degrees. And this means that this is the point at which sunlight impinges most directly. This will be the point at which solar heating is most intense on Earth. And as the Earth continues its orbit around the sun, or equivalently, as the sun continues its path around the celestial sphere, it again reaches an equinox on September 21st, at which point the line separating light from dark passes through both poles. The sun is overhead at the equator, and night and day are of equal length everywhere on the planet. And as the sun continues its path to its December solstice, in December, the sun is as far south of the celestial equator as it gets. It's at a declination of negative 23.5. At this point, the sun is overhead at a latitude of negative 23.5. The entire Antarctic Circle, latitudes within 23.5 of the south terrestrial pole, have 24 hours of sunlight, and latitudes to within 23.5 of the north terrestrial pole have 24 hours of dark. The sun never rises in the north and never sets in the south, and maximal heating is at southern temperate latitudes. And I hope that this picture, if you play with it a little bit, will clarify the relation between the orbit of the sun around the celestial sphere, the tilt of the Earth's axis relative to the sun. Note that the Earth's axis points in the same direction towards the celestial North Pole as the Earth rotates around the sun, and the changes in length of day and night and in terrestrial heating. So let's summarize this. Let's summarize what we've learned. Between March 21st and September 21st, the sun is north of the celestial equator, increasingly so until June, and then decreasingly so from June through September. And then from September through March, the sun is south of the equator, increasingly so until December, and then decreasing from December through March. When the sun is either, say, to the north of the equator, then days are longer in the northern hemisphere, and the sun is higher in the sky in the northern hemisphere because its declination is closer to the declination of your zenith if you're in the northern hemisphere. We saw that your zenith is located at a declination equal to your latitude. The sun will get closer to that zenith at its highest point if you're in the northern hemisphere when the sun is north of the celestial equator. And we saw that the sun's rays impact the Earth more directly in the northern hemisphere, so climate is warming in the north and cooling in the southern hemisphere. And of course, the reverse is true from September to June when the sun is south of the equator. Inside the Arctic Circle, at least for some part of that time, the sun becomes circumpolar. The sun comes so far north that it's close enough to the celestial North Pole never to set for regions north of the Arctic Circle for at least one day. Of course, at the precise North Pole, the sun is circumpolar for 6 months. For precisely 6 months, so long as the sun is north of the celestial equator, the sun never sets at the North Pole, and the sun never rises at the South Pole. And then the inverse is true as when the sun is south of the celestial equator. And twice a year at the equinoxes, March and September 21st, day and night are of equal length everywhere. And then there are these two tropics, 23 of latitude plus or minus 23.5 degrees. If you live somewhere between those two tropics, there will be some day a year when the sun is directly overhead at noon and passes through your zenith. The sun, interestingly, is over only at your zenith, directly overhead on the equator, precisely on the equinox. Let's apply what we've learned to answer the question how high the sun is at noon. And since we've started with Aristotle, let's continue with Aristotle. We'll be working at Athens' latitude of 37.7 approximately degrees north. Remember that noon is the time when the sun is highest in the sky. That's its meridian crossing. And so its altitude or its zenith angle will be determined precisely by the sun's declination. At the equinoxes, March or September 21st, the sun's declination is 0 degrees. Those are the days when the sun crosses the celestial equator, and for the course of a day we can imagine the sun fixed along the celestial sphere because it only moves by about 4 minutes along the celestial sphere. And if the sun is at declination 0, then at noon its zenith angle is just the difference between its declination and the declination of our zenith, which is given by our latitude. Its zenith angle is 37.7 degrees, which means its altitude is 90 degrees minus 37.7, which is, I believe, 52.3 degrees. At the summer solstice, and the summer solstice is June 21st, so this is the northern summer solstice, the sun has reached a northern declination of 23.5 degrees north. The zenith angle, therefore, at noon, is the difference between our latitude and the sun's declination, which at this point is only 14.2 degrees. So at noon in midsummer, the sun in Athens will reach an altitude of 75.8 degrees in the sky. On the other hand, on December 21st, the sun's declination is now negative 23.5 degrees. So its zenith angle, when it's as high in the sky as it gets, at its meridian crossing, is the difference between plus 37.7 and negative 23.5, which is, if I got it right, 61.2 degrees, which means the sun's maximum altitude in the winter is only 28.8 degrees. You note that the solar heating in Athens is minimal in December 21st. December 21st is not by far the coldest day of the year in the Northern Hemisphere. The coldest day is usually somewhere around February. There's something like a thermal inertia. It takes time for the Earth to respond to the change in solar heating. There are many other complicated factors that govern climate, heat exchange between the equator and the poles and so on. But to a good approximation, solar heating is maximal at the summer solstice, and therefore in June, and about 2 months later in August, the temperature has reached maximum. By that time, solar heating is in decline, and with the same 2-month lag, the Earth starts cooling off. Solar heating is minimal in December, all this in the Northern Hemisphere. Of course, everything is reversed in the South, and 2 months later, the Earth is as cold as it's going to be. And while we're discussing solar days and the Earth's orbital motion, there are two other small imprecisions in what I said that I need to correct. One is, I said that 24 hours are adjusted to be a mean solar day, and you can ask, what's so mean about a solar day? This was mean in the sense of average. It turns out that solar days are not all the same length. Why is this? Well, the Earth's rotation about its axis is extremely uniform. We'll talk later about how it fails to be uniform, but it's almost exactly uniform, certainly on the levels of precision that we're talking here. So the length of a sidereal day is very constant. The length of a solar day is not. Remember, the difference between a sidereal day and a solar day is associated to the sun's motion along the celestial sphere. The sun moves to the east by 4 minutes every day, and therefore there is a 4-minute difference between solar and sidereal days. But the sun's motion to the east along the celestial sphere is not uniform. So the first cause of this is that the sun moves uniformly. If the Earth orbits the sun uniformly, then the sun would move uniformly around the Earth, but it would move along this tilted path of the ecliptic. What this means is that near the equinoxes, the sun's motion is not parallel to the celestial equator. It's not purely in right ascension, it's also changing declination. Whereas near the solstices, the sun's motion is parallel at the maximum and minimum. The sun's motion is now parallel to the celestial equator. And so its motion in right ascension is slower near the equinoxes and faster near the solstices, and the 4 minutes is an average. And that is one reason why the length of solar days is not uniform. There's another correction to this. In fact, the rate at which the Earth orbits the sun, or equivalently the sun orbits the Earth, is not precisely uniform even along the ecliptic. This is because the Earth's orbit is not precisely circular, and the Earth is in fact very slightly nearer the sun in January than it is at any other time of the year. At that time, the sun's apparent motion in the sky is fastest, and 12 months later, it is slowest. And so, even along the ecliptic, the sun's motion is not precisely uniform. Moreover, I kept talking about the fact that the Earth's North Pole maintains its orientation in space as the Earth orbits, so that it always points in this direction of the celestial North Pole, where sits some particular star, say the pole star. And this, it turns out, is also inaccurate. We are building up more and more precision into our model, and in fact, the Earth is spinning about its axis. It's acted upon, as we will see, by the sun and the moon applying tidal forces, and like a spinning top spinning on a table and acted upon by gravity, the Earth's axis wobbles in the same way that a spinning top wobbles, except it's a little bit tricky. A spinning top will wobble in the same sense in which it is spinning. The Earth's polar axis actually wobbles in the opposite sense to the sense it rotates. In other words, the celestial North Pole moves to the west along the celestial sphere. So the Earth's North Pole does not always point in the same direction as I've been saying so far. Instead, it's tilted by 23.5 degrees to the orbit, but as the Earth rotates to the east, the celestial pole very slowly wobbles in a big circle in the sky of radius 23.5 degrees about the perpendicular to the orbit. And this wobble, called the precession, takes about 26,000 years. What that means is that the point that we define as the celestial North Pole moves with time. And what this means is that what we now call the pole star will in a few thousand years no longer be the pole star. The Earth's North Pole will face in a different direction. More intriguingly, the celestial equator changes. As the Earth wobbles, the tilt of the celestial equator relative to the orbit, or of the ecliptic relative to the celestial equator, is always 23.5 degrees, but at different orientations. What this means is that the equinoxes, the hinges at which, the points at which these two circles are hinged, move around the celestial equator. Hence, this whole wobble leads to what is called the precession of the equinoxes. If the vernal equinox shifts, then the coordinates of all stars shift because the origin, the intersection of the equator with the meridian including the vernal equinox, moves. And so the coordinates of a given star change. This is most clear if you think about it. The star which now has celestial coordinates declination 90 north, which is the North Star, will not have those same coordinates for very long as the Earth continues to wobble. And so when you look at right ascension and declination for a given star, they will be given in terms of some epoch, most typically epoch J2000. That means these coordinates are given relative to the position of the celestial equator and the vernal equinox as of the orbital parameters on January 1, 2000. Back in Athens, it's still November 27th. What I've done is I've attempted to have the software keep us centered on the North Celestial Pole so that we will be following the North Celestial Pole as time goes on, and I will make time move by centuries. And what you will notice is that over time, the celestial pole moves. The celestial pole started out very near this pole star of Polaris, and the celestial pole moves, and it moves in this great big circle in the sky, so that by the time you get to 10,000 or 11,000 AD, Vega is closer to being a pole star, and of course in 26,000 years, the pole star will, the celestial pole will have completed its wobble, and we will again have Polaris as a good North Star. Let's try to see that again, and at this point, we should pay attention to the position of the vernal equinox. Of course, as the pole star moves, so too does the vernal equinox. Remember that it is currently in the constellation of Pisces. You can see that it's moved quite a distance along the equator. Remember, it completes a full circuit of the equator, and over this time, and I'm now dialing time back to the present, and the vernal equinox is moving to the east along the celestial equator, and as we approach the present, we find that around the present, 1,000 years ago, the vernal equinox is indeed in the constellation Pisces, and as you move time forward, you will see that on or about 2600 AD, the vernal equinox leaves the constellation of Pisces and enters the constellation of Aquarius. That means we are currently living in what is called the age of Pisces, and as of 2600 and some, we will be in the age of Aquarius. If you look at 22,000 BC or so, the time that pyramids in Egypt were being constructed, the North Star that we use today was nowhere near the North Celestial Pole, and in fact, dating of pyramids is based to some extent on astronomical conjectures of what it was the Egyptians used as a North Pole, and there's real information to be gleaned from this wobble of the Earth's pole. We started out trying to understand which stars were going to be visible when. This was in itself enriching. Along the way, we figured out the reasons for the seasons, and we started investigating the sort of arcane phenomenon of the wobble of the Earth's axis and the precession of the equinoxes, and came up with an understanding of ways to date Egyptian pyramids based on which North Star they align to. So we're making progress in understanding the moving parts of this model of the universe that we're constructing. The most conspicuous absence is the moon, and it is to that we turn next.